Okay, I haven't shared my screen. Let me share my screen. Um, 1 second. Share. Okay, let's continue on to the third question. So for the third question, we have the question concerns n times n matrices where they are represented by the type below as in rows where each row is a list of type of n elements. So we have this form of type matrix is just two lists, one list of integers, and then they're nested in another list. And then for I greater than 1, we will often refer to the ith element of the list with the understanding that I is equal to 1, which corresponds to the head of the list. So in this question, we can't use this to access it. Um, so the first function asks to define a function get such that for I greater than 1, get I excess returns the ith element of excess if such an element exists. The function should be undefined, otherwise be sure to explain why your answer meets the criteria. So we have this type, we get an integer from a list, that's our two inputs, and then we return if it exists. Okay, so we put in what we get our index from this list, excess, um, if I is equal 1, so like we would just give out the first head. If it not, we're just gonna call it once more with a smaller decrease I by 1 and then just call it on the excess. So basically we're just moving the index one by one recursively. And in the case that it doesn't work, we're just going to say that it's just error because we can't get anything out of it. So I wrote the explanation here. We try to pattern match from to I to x of x's. If I is smaller than 1 or empty, then we have the error, else we recursively find index by calling get. Yeah, we didn't use this because we actually recursively found the definition for that. Okay. Moving on to part B. Using explicit recursion, define a Haskell function omit that takes the list and then returns a um, nested list that given an input list of size n returns another list of size n such that for all 1 smaller than or equal to I, smaller than or equal to n, the ith element of the output list is equal to the input list with the ith element removed. So for example, omit 0, 1, 2, 3 gives 1, 2, 3, 0, 2, 3, 0, 1, 3, 0, 1, 2. So we're just basically every time removing one thing. So like the first list is removing 0, the next one's removing 1, the next one's 2, the next one's 3. So all of the things. So determine whether this function can be defined as an instance of float. Okay, this is a pretty big function that we need to write. So here we just had to find it recursively. So we're given this is a type they gave. Next, we know that if it's empty, we do need to return empty. Let me double check on this. Because I feel like if I'm returning this, yeah, I think it works. And if we have omit, then omit x of excess is equal to the excess of map. So like we just basically take out the first element, then map the remainder and just call the omit function once more. So the idea is that whatever x is, it's just in the front, and then we just call the omit functions that we get what we need. I think this is a really, really neat way of actually doing it because essentially, like if we think about it, like if it was 0, it would make sense that 0 would appear at the beginning. We would just map it again. But um, kind of, I definitely did not think of this during the exam. Is that like you can use map really, really well and recursively because like if it was empty, then we'd return empty. Otherwise, we would put it in the front. So then I don't know. This is just, I kind of need a better explanation than this. I think it's better that I just type it up and ask what is like the actual legit way of actually explaining it. But I don't think my answer is really well written out. So I'm gonna ask AI to write a better solution than what I gave. And obviously before I thought that it could have been implemented, but I don't think it's possible because um this would have to use like the original list and the list so far, which is kind of like, guess it's not the best way of doing the question, and it definitely misses cases. Okay, so this is part A. I'll include part A here. Um, I'll include it on the side, read this side. So we first have a omit function, and our base case is empty, returns an empty list. This is pretty straightforward. For a list of x of x's, the first element of the result corresponds to removing the current head x, which leaves us the tail of x's, right? So if that's removed, then we're just calling the rest. And then the subsequent elements correspond to keeping the x and removing the element from the tail of x's. So we can get this by taking the recursive result of omit x's and putting x back onto the front of each list using max map. So this is the case. So every time what this means is that we're gonna have a list, right? We're gonna have the head of the list. We get either first, and then this is the remainder of the tail. Let's call this tail. So what we do is essentially we first remove the head, so we just keep the tail. That's the first valid operation of removing the heads, right? And then after that, the sequences should just be, we should have the heads in front because that's always in the front. But then we're trying to remove some element from tail. So then that's just essentially the recursive definition. So that's just omit of the remainder list, which is the x's. So that's how we get this recursive definition. I think it's just so neat that you can just do that. And this, just writing this out using notation, is this map of x. That's essentially how you do it in Haskell. So that's really, really neat, I say, just of being able to write this out. And then in terms of why it's no, we can't write it as a fold. Uh, Let me paste this thing over and now explain. I think it's much better written out than I did because I got it. On the actual exam, I did get it right, but guess it has to be standardized. So the standard fold function has this structure. We want to write it that way. We have current value x, and then we have the omit x's. But we realized that inside here, we're looking at omit x's, and the x's makes us really uncomfortable because what we essentially have is like omit x's is our accumulator. But at the same time, we also have to use x's, which is our tail. But fold only gives us omit x's and not x's. So then that means that we cannot write it in terms of fold because of that. So yeah, because it does not have access to the tail x's. Um, a counter example is, let's say, it gave omit 1 results in this, omit 2 also results in that, but because f only sees a current element and the result this, it does not know whether to reconstruct 1 or 2 by placing it at the head of the output list. I guess this makes sense because, yeah, essentially what we do is if we have 1 or 2 and we don't know what to keep track of, then mm, then there's kind of no way to reconstruct it back. So I think any element essentially works. Okay, moving on to the next question. Part C. Given an n times n matrix M, one can compute a determinant using the Laplace expansion along row I. As follows. So this expression where AI is the entry at the intersection of the ith row and the jth column of in M, and Mij is a matrix obtained by deleting the ith row and the jth column from this. We're trying to find the function minors that given I in M returns the list of this thing. So the idea behind minors is we want M1 to Mi to N. Okay, I think yeah, I'm gonna have to get a better answer than this. This is not great. My work was not the best, so I'm gonna get something nicer. I feel like this is just a linear algebra question, and then I feel like the top part actually isn't used until part D, which is kind of I think they didn't organize that well, but I guess it still works out. So, I asked them to go with what I did. They didn't their generated thing is kind of so I'm gonna have to work it out there. I think the main takeaway from this question was that I in the exam tried to redefine C using split, take while, drop while, and those functions. Whereas the major thing that makes C simple and easy is actually using the omit function we just wrote in part B. Because like with the omit function over here, it makes life a lot easier. So you don't have to necessarily do that. Okay, Gemini is not cooking. Its generative content is really bad, so I'm trying to get something that's better and clearly explains the thing concepts. Because right now the code it's generated is very um different than what I did. So let's see if it's good or not before I put it here. Um, this one's okay. I can put it over here. So the first part it did was I asked it to explain what the question was asking for in more detail. So we're trying to input this function that's called minors that generates a specific list of submatrices. Um, Here we input a integer I for that specific row, and then we're just trying to um, so the idea behind this is that we're trying to create the minors. The minor would just be everything except that thing. So like if we have a matrix, something like this, and something like this, then we're just trying to create something that does not contain this row and this column. And then we're just trying to iterate it so that in for the specific row that we pick, let's say if we picked this row, then we're just basically iterating through the columns and removing each column once, and then the row obviously is always removed. And then this would be our list of our minors from 1 to n. So we have removed the columns n times, right? So that's basically what we're doing. And then the code, yeah, guess it's not the best. I'm gonna just explain through it, I guess. So we have the integer of the matrix, and then we have our input of the I and the M, which is our matrix. And we just define stuff. Let rows reduced equals get I of omit M. So this is just basically, we're just trying to get all the rows. So we're just taking all of the rows here. And then we're just omitting the M, which we just defined. So we're just basically getting everything except this one. That's pretty straightforward. Um, N is equal to the length of head of M. So because we define N, this is a matrix, we just take the first list inside this matrix. And then we just take, because head is just the first one, and then we just take this length. So then we would get what our N is, our size of the matrix. And the next, what we do is we want to actually get what this actual matrix is, right? We want to construct it. So we want to, every time we want to iterate through the columns each one by one and remove them independently. So we have get j, omit row. That's pretty straightforward because we do want to make sure that the rows are reduced. And then we want to go from, for every row, in row reduced, we want j from 1 to n. Okay, I guess I'm gonna create something here. This would better explain what my code does. Because it's kind of hard to just explain it without any kind of help with diagrams and or explanations. So here, I think it's much better written out than I did. The first is rows reduced, then it's like this thing over here. So the rows reduced is that because we know that we have the ith row removed, we do this every time. So essentially that's what we do. Yeah. And then we just use omit m and then we get our I row gone. So this is just the n times I, n times 1 times n matrix. So like we, as I explained earlier, this is just the row removed. And then next we have the step 2, which is generating the list of minors. So we have the index j. And what this j does is it's like the loop of the column index from 1 to n. So that every time we're just going through and deleting one column. So how we delete that column is inside here, we have to remove the jth element from every row. So what that means is we go into the row. For that row, we get j, and then we omit that row. So that's how we get the column. So it's mainly because of how the array is stored. Like if I was to draw a picture of the array, how the matrix is set up is that we have within this we have each row stored as the stuff like this. And it goes on and on and on until this. And initially it's a matrix like this, then it's a square matrix. We know it's n times n. What we do is our first operation is we pick the I row that we get, and then we use get and then omit. So we make sure we pick the row that we're dealing with, and then we make sure we delete it. So then what we get next is a n minus 1 matrix. And then this is still n. And then next what we have to do is we have to kind of write that iteration of like then what was it called? I can't even remember what that this inside the list comprehension. Yeah, list comprehension. We have to use list comprehension to basically iterate through each of the remaining rows from 1 to n minus 1. In each of the rows, you have to iterate and make sure that we remove the we just get this and make sure that we omit this element that's part of this column. And we iterate through the columns from 0 to n. So we make sure that everything from here is taken out, and then make sure that each time we're iterating through that. So that's basically like a for loop, but done recursively in list comprehension. So that's what the code here does. I think it's really, really neat in the way it's written. And part D, define determinant of matrix integer that calculates the determinant of the input matrix by repeatedly applying Laplace expansion along the first row. Okay, so this is just basically we're just setting this to be the first row, and every time we see that, we get our matrix from we do have the determinant. So like in linear algebra, I would like to say that like once we do the operation, we would end up essentially with n times n of this. And because we applied it on the row, in Laplace's formula, what we essentially do is that each squared is sign, plus or minus, alternating. The first one is positive based on the coordinate of I and j. This is I plus j. And if it's even or odd, it's positive or negative, depending on that. And then for each of the n minus 1 matrices, we do want to find their determinant. And then once we find the determinant, we just plus and minus them together. So that it's just a recursive process of like first from the n times n we create n minus 1, n minus 1, and we create n of this matrices. We create n of this, n copies of this, different of each row, like each column removed. And then next what we do is for each of those we would have n minus 1 matrices of size n minus 2 and n minus 2 and so on and so forth. And we would still apply it on the first row to find each one. And we just do it recursively until we only have one matrix. That's 1 by 1. So whatever that value is our determinant. And then we substitute that value back in, and then we make sure that we account for whether it's plus or minus over here. So essentially we have the determinant. This goes from a matrix to integer. That's pretty straightforward. If it's a single matrix, as I said, 1 by 1 matrix, we know that it's just that value inside. And now we go through the recursive process of our matrix, and now is equal to the sum of terms where row 1 is equal to head of m. So then we have ms is equal to minors of 1 to m. So we're just doing it on row 1. And then our signs is cycle 1 to -1. So this creates an infinite list of 1, -1, 1, -1, which matches our like checkered pattern over here in the first row. And then what we do is we use terms is equal to zip with 3. So zip with 3 is just we have 3 variables and we want to combine them together. So we're going to define S, A, and M. And what we're going to do with S, A, and M is that we're going to make sure that we times S, which is a sign, times it to A, and our determinant M, whatever it is. And then our input is the signs, the row, and then the MS that we created, the minors. So that's basically the recursive definition. And we're going to get each one just created together and we're going to get those. And then it's going to be summed together and combined together. I guess that's the idea of determinant is that we kind of break it down into pieces. Each time recurse it down to a smaller case, and then we make sure that the smaller cases gets combined back up together to prove what we need. And then the last question, part E, write a Haskell program that, given f, takes from integer to integer to integer. As an input, computes the infinite matrix M matrix such that for all I greater than or equal to 0, j greater than or equal to 0, we have M of I of j is equal to Fij. So this basically means that we do want to access the elements. So we define our infinite M to be this thing where our F just takes two integers and returns integer, and then we're given the matrix. I kind of need a diagram. Maybe I should ask Gemini to see if I can generate a good diagram. If not, I'll draw it out afterwards if it doesn't work. Okay, let's see if it can do it. Otherwise, I'll do it later. So the idea behind this is this list comprehension going from 0 to 0. The idea is that we want to make it accessible when we go from infinite. So while Gemini is generating, if it's not good, then I'm just going to go with my explanation. So the idea is that if we kind of just generate a list that goes on forever, then we're kind of problematic, right? If we go something like this, then this goes on forever. So we're never going to be able to access something over here because this goes infinitely wide. So something we have to do is um, kind of put a limit on the thing. So like for instance, if we enumerate something, then we kind of have to hard cap it. So then if we go from I to from 0 to like I don't know, if it's 0, then this one has to stop here. Then this one has to stop here. So we're basically just putting it like that, accessing it like that, so that we make sure that we don't exceed the limit and that it could access everything. You know what? I don't even need to go with this approach. I think it's just easier if we just say that this is just like the typical, I just create an infinite, I create an infinite, I get what I need. I think that's basically what it does. Because Haskell, this is just basically because Haskell is lazy. Okay, so here I'll provide the code and explain it through. Okay, so I have this. This is my what I wrote. The explanation is understanding list comprehension and lazy evaluation to construct infinite. So this notation constructs everything from 0 above, and Haskell doesn't generate this. It's lazy, so it only does what it needs. So we first generate from I, which are the rows. Then for everything we create um, the J, which are the columns, and it goes from this. And the Fij is used to calculate. This is just M of I of j is this. So when we call this, we want to make sure that Haskell goes from the ith element to the jth element, so it creates this perfectly. So yeah, that's how we just generate. Just say that we're gonna create this that goes to infinity, create this that goes to infinity, and no matter what, okay, yeah, there's gonna be some value. We're gonna only bother evaluating it if we're needing it. That's basically the idea. Okay, this functional programming test was kind of difficult, even though I corrected it before. I feel like it's been for a month since I did it, so I kind of don't remember what was going on. I should have definitely looked at the questions first before I recorded the videos, but yes, it's good that it kind of forces me to think on the spot. And I definitely learned several things and reviewed several concepts as I walked along. I think for question one, it was unfold. For question two, it was kind of just walking through the invariants and knowing that I need to write auxiliary functions to help me make the process simpler. And for question three, I think the major difficulty I had was the infinite and the determinant part of like using the get and omit to actually write what I need.